Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 24, Object3D Classes, Scene, Group, Camera, and Mesh. So, starting in this video, we're going to begin to implement the class framework structure in code. The first, most important class is going to be the Object3D class. To review, it represents nodes in our scene graph, which represents objects in the world. And there's three main pieces of information the Object3D class needs to store. A matrix, to store its local transformation data, a list of references to child objects, and a reference to a parent object. It'll also need some functions, add and remove functions to update references to the parent and child objects. A function called getWorldMatrix, we'll use that to calculate the world transformation. GetDescendantList, which will kind of collapse the tree object into a list, which will make it easier to iterate over the object later. And for convenience, we'll also add some transformation functions which generate and apply the transformation matrices that we set up in an earlier video. So to begin, I'll go ahead and open up Sublime Text. And this is definitely a core class, so I'm going to right-click and make a new file in the core directory. And I'll immediately save this as Object3D. All right. Mostly, the only external class we need is the matrix class. And as you might recall, the matrix class just has a bunch of factory methods to generate NumPy matrices for us. So, to begin, we'll need an import statement from core.matrix, import capital M matrix, and then let's define class Object3D. Extending object. We always need an initialization, and we'll define those three pieces of information. The model matrix. I'll start off with the identity matrix. Parent. Initially, we're not sure what the parent will be, so we'll say that's equal to none. And a list of child objects, we'll call that children, and initially that's an empty list. All right, next we're going to need some add and remove methods. They're pretty straightforward. All right, so add self, we're going to add a child. So again, there's two things we need to do. And I want to keep the child and parent references in sync, and that's why these functions are fairly useful. So we don't forget to apply the changes to both the relevant child and parent fields. So first, if I'm adding a child to this object, well, to the children list, I want to append the child. And then this node becomes the parent of the child that's being added. So we'll also say child.parent equals self. Similarly, we'd like a remove function. So we'll say define remove. And basically, we're doing the opposite of what we did before. We'll say self.children.remove. We'll remove the child from the list of children. And we'll also kind of nullify the child's parent. And so there's no dangling references. So instead of self, now it's none. All right. The next function we discussed adding was to get the world transformation, or the world matrix. And remember, that calculates where this object is relative to the root of the scene graph. So we should definitely add a comment to that effect. We're going to calculate the transformation of this Object3D relative to the root Object3D of the scene graph. So we'll call this def get maybe world matrix. Let's see. This kind of has to be a recursive method, right? Because we don't know how many ancestors there are between this node and the root node. So we'll say there's really two cases. If we're at the root, and that's distinguished by there is no parent, well, then we're done. We'll just return this object's transform matrix. Otherwise, well, there's still something left to do, and we'll return, well, we'll get the transform matrix of the parent and multiply it by this object's transform matrix. So self.parent.getWorldMatrix times, and NumPy uses the @ symbol for matrix multiplication, not the asterisk, but the @ symbol. We have to remember that. Times self.transform. All right. And that's how we can calculate the world matrix. It's short, but we have to think about it for a minute because it is a recursive function. It calls itself. All right. Our next task is going to be to flatten the tree structure into a list structure. Right, so the next function, let's write a comment. We're going to return a single list containing all the descendants. Right, and we'll give it the name getDescendantList. So def get descendant list. All right. First, let's define maybe a master list of all descendant nodes. Descendants. All right. So this will be initially an empty list. And then we'll create, this is going to be, we've got to traverse the tree. So depth first search. So we're going to do nodes to be added to the descendant list, whose children will be added to this list. All right, so first I can populate this with, let's call this nodes to process. All right, so I need to add this node itself to the descendants list, and then I need to add all its children to the descendant list. So let's do that. And again, I'm not sure how long this is going to take. So I'm going to use a while loop here, and I need to continue processing nodes while any are left in the list. So while the length of this list, the nodes to process, is greater than 0, while there's any left, first we're going to remove the first node from the list. Right, so I'll say node is equal to, take that list, nodes to process, and we'll pop off the one at the first index. Then we'll add node to the descendant list. So descendants dot append that node. And then we need to take all the children of this node and add it to the list of nodes to process. So again, the comment there is children of this node must also be processed. So we'll say nodes to process is equal to, well, first, whatever's already in that child list, and we're going to add that to nodes to process. And based on the order in which you add, you can kind of tell this is a depth first order traversal of this tree, because the children of this node are being added in first. So when we go back through this while loop, the children are going to get processed before anything else in the list. So we're going all the way down to the leaves of the tree before we go across. That's it. That's how tree traversal works. When we're done, we just want to return the list of descendants. And that's it. That's that function. Now, the other set of functions we really want to include, just for convenience, we'd like some functions that automatically translate, rotate, or scale this object. And as we discussed in a previous video, we can also do that globally or locally. So we want to have as much flexibility as possible. So we're going to set up a bunch of functions, basically. So you don't need to know the name of the methods in the matrix class, and so you don't really have to import the matrix class at all. You can usually just use these methods we're building into the Object3D class. All right, so some more definitions. And these all fall under the heading of apply geometric transformations. All right, so we'll start with the most general one. We'll call it apply matrix. We're applying it to the self transform, applying some matrix named matrix. Also, again, I want to know whether I want to treat this as a local transformation or a global transformation. And we'll have it set default to a local coordinate system. So that'll be indicated by that Boolean function. So if this is a local transformation, then the new transform matrix, the new model matrix, and remember, for a local transform, we want to multiply the new transform on the right. Else, it's a global transform, in which case we've learned that we implement global transforms by multiplying on the left. All right, cool. So that's the general apply matrix function. Now we're going to want individual functions for translation and all the different kinds of rotation, and these are all going to look very similar. So let's see, we'll start off with def, let's call this translate. You translate according to x, y, and z values. And again, local coordinates defaulting to true. So really there's two steps in each of these functions. First, from the matrix class, create the specific kind of matrix that you want. In this case, to translate, I want to make a translation matrix. And then I want to apply that matrix, so applying the matrix M, according to whether or not it's local coordinates. And that's it. Now we just need to do this a bunch of times. So let's define maybe rotate X, self, this requires an angle, and again, local coord defaulting to true. I'll create the matrix. M is the matrix make rotate X, rotating by some angle, and then self dot apply matrix M local coord. Now I need this three different versions of rotation, right? We're going to rotate around the x-axis, y-axis, and z-axis in general. So I'll just copy paste that twice. In the second function, I'm going to change that x to a y there, change the x to a y here. In the last function, I'm going to change x to z and change x to z. So there we've got three different functions for rotating the object around the x, y, or z axes. The last one that we're going to use is let's define a scale. And if you want to scale something, again, we're really only going to need uniform scale. So it's just taking a single parameter, right, in accordance with what we did in the matrix class. And once again, self.apply matrix, and apply M, like so. All right. Now, for convenience, there's one really great thing about using matrices, using 4x4 matrices in homogeneous coordinates. Even though it's really hard to read off the rotation and scale data from a transform matrix, it's really straightforward to find out where your position is. All you have to do is look in the rightmost column, and the rightmost column is your X, Y, and Z position. Those first three entries. So it will be convenient if we write the following methods, functions, to get and set the position components of the transformation matrix. So I'm going to treat that like a vector. The hardest part is really figuring out what the names of the methods you need from the NumPy library are. All right, so to get the position, I'm going to return this as a 3-component list. All right, so self transform is the matrix, and to get the element in the row 0, so I start counting at row 0 and column 3, and that's the syntax for that. And that's the X component of the transform. Then the Y component of the transform is in the second row. And the Z component of the transform is the item, at third position. That's how you can get the position out of a matrix. Or in general, how can you retrieve an element at a certain position in a NumPy matrix. All right, finally, let's also do a set position. Now in this case, this needs parameters, x, y, and z, but will not have a return value. Self.transform to set the value at a position. You might notice they're called items up here. There's a function called setItem, or no, I got that backwards, item set. It takes 2 coordinates. First, you need to know what position, and second, you need to know what the value is. And for convenience, I'll copy-paste that. Y and Z. All right, so at index 0, 3 in the matrix, we'll set that to the value x. At position 1, 3 in the matrix, we'll set that to value y. And at position 2, 3 in the matrix, we'll set that to value z. Cool. And that's the Object3D class. We're going to get a lot of use out of this class. It's kind of the root object for many things. Now, while we're talking about Object3Ds, we're also going to do the different extensions of this as well. Let me go ahead and save that. And now I'd like to create the extensions. So let me go back to the presentation. All right, so we talked about Object3D. First, let's do scene and group. Scene, as we discussed before, represents the root node of the tree, and group represents an interior node. These don't really add any functionality. Their purpose is just to make code easier to read, which is important. We could theoretically get away without defining these, but let's add them just so our code reads easier. So we're literally creating 2 objects which extend the class, call the constructor, and do nothing else. So let's go back to Sublime Text. And in the core folder, I'm going to create a new file. This first one, go ahead and save it right away. This one we'll call scene.py. So from core.object3d, I want to import Object3D, class scene. It extends the Object3D class. To initialize this object, Well, from the superclass, call its initialization. That's it. Seriously. All we want is a specially named Object3D. All right, let's save that and let's create the group class. So again, this will go in the core folder. I'll right click and make a new file. Immediately save it. This one I'm going to call group.py. And the same code as before. From core.object3d, import object3d. This class is called group. It extends object3d. Defining the initializing function. From the superclass, call the initializing function. The end. All right. Again, the code will read much more nicely if we create scene objects and group objects. Just by reading that code, it'll be clear what the intent is. Next, let's go back and see what the next class we have to make is. So the next class is going to be the camera class. The camera class is interesting. It represents the virtual camera that's used to view the scene, but the camera isn't a physical object that's rendered. It has no actual appearance in the scene. And cameras, they require a little bit of thought because they do something to the scene. The camera transform is going to affect the placement of the objects in the rendered image of the scene. Right? So when we talked about creating a projection matrix in a previous video, we assumed that the camera was located at the origin and looked down along the negative z-axis. The camera class is going to enable us to put the viewer at any point, not just the origin, and look in any direction, not just along the negative z-axis. But how is that going to work in practice? And so the key here is to consider an example. So consider these two different things which could happen in your rendered image. Imagine you have a camera and you shift the camera to the left, and imagine how that would change the appearance of your scene if you shifted the camera to the left. Now, also imagine, what if you didn't shift the camera to the left and instead you shifted the objects in the scene to the right? Now, those two transformations are what we would call equivalent. They result in the same rendered image at the end of the rendering process, and there's no way to distinguish between them. If you were to shift the camera to the left by 2 units, or to shift objects in the scene to the right by 2 units, the results are going to be identical. And the point of this example is to illustrate that every camera transformation will affect scene objects in the opposite way. If you'd like another example, imagine if you had a camera and then you just rotated the camera by 45 degrees. Or compare that to the result of keeping the camera still and rotating all objects around the camera by 45 degrees in the opposite direction. Again, rotation of the camera in one direction corresponds to rotating everything around the camera in the other direction. And every camera transformation affects scene objects in the opposite way. And so, this leads us to, we'll mathematically think of this as the view matrix, and it's really just the inverse of the camera's transform matrix. And so when we render an object, we'll apply its model matrix, so we know the object's perspective in the scene, or position in the scene. Then we'll apply the view matrix, which kind of aligns every object with respect to the camera, and then we'll apply the perspective projection. We're getting a little bit ahead of ourselves now. That's just something we have to look forward to. But the idea is every camera will have a view matrix, which is the inverse of a camera transform matrix. And since cameras also kind of show us how we see the world, it also seems like a natural place to store the projection matrix as well. So those will be the two pieces of information we want to store within the camera. It's the projection matrix and the view matrix, which is the inverse of the identity matrix. I mean, the inverse of the transformation matrix. So to implement this, it takes longer to explain than it does to implement. Let's head back to Sublime Text, and in the core folder, let's make a new file. I'm going to save this one as camera.py. All right, so we need a few things from, well, since this extends Object3D, of course we need to import Object3D. We also, we need to use a projection matrix here, so we actually need to import the matrix class as well, which we'll use to generate a projection matrix. I need to make sure that M is capital. And finally, to perform the inverse transformation, this is something where we're going to use a built-in function from NumPy. So from NumPy, it's linear algebra package, linalg, import inv. This calculates the inverse of a matrix. So the class is called camera. It extends Object3D. First thing is to create the initialization function. We'll have it pass some parameters, the parameters used to define the projection. And so these are angle of view, and we'll give these the same default values we did previously. Aspect ratio, near distance, and far distance. I think something like that. All right, so those are the initial parameters. First, let's initialize everything in the Object3D class. So calling super.init. And then let's set up those two matrices, the projection matrix. So we'll say self.projection matrix from the matrix class. Hey, matrix class, please make us a perspective matrix. And the parameters here are angle of view, aspect ratio, near distance, and far distance. We also need the view matrix. Initially, we'll say that's the identity matrix. Matrix.makeIdentity. And now, there's two ways we could go about this to get the view matrix. Remember, the view matrix is the inverse of the model matrix or the transform matrix. We could just create a method called getViewMatrix, and that calculates the inverse of the transform matrix. But it's really computationally intensive to keep calculating the inverse of the view matrix every time we need it. So instead, when we need the view matrix, we'll just kind of get it directly from the field in the camera object. But I still do want to invert a matrix, so we'll create a method called updateViewMatrix. Again, this is really used for performance considerations. So when we update the view matrix, we're really just calculating the inverse of the transform matrix. Now, it might be tempting to say, well, self.transform, but we also want to keep in consideration, what if the camera matrix happens to be attached to something in the scene? What if the camera is not attached directly to the root? You know, maybe we've connected the camera to some kind of a movement rig or some kind of third-person object which is moving around the scene. So instead of self.transform, we actually want to use getWorldMatrix. Right, so that'll take into account anything the camera may or may not be attached to. So that's the camera class. Now, one more class I'd like to write the code for while we're here, since we're extending the 3D objects. I'd like to set up the mesh class. Again, mesh, since it extends the Object3D class, it stores a transformation object. It's going to store instances of geometry and material objects, which we will create in a future video. Stores a vertex array object, which connects these two, geometry and material objects. And for convenience, we'll also put in some kind of a visibility variable, a Boolean, which will determine whether the object should be rendered or not. Right? And this could be useful if you had some objects which started out as not visible and become visible at a later time. Really, the only task we have to worry about is setting up the associations that the vertex array object stores. Right? So there's an association between the vertex buffers, which are stored in attributes in the geometry, and the shader variables, which were stored in the shader program within the material. And so we'll perform this task in the mesh class. All right, last class. So in core, I'm going to create a new file. This one is called mesh.py. All right, I want to make sure I save camera as well. Save. All right, for the mesh class, again, we're extending Object3D, so from core.object3d, import Object3D. Also, we're going to be setting up a vertex array object, so we need access to the OpenGL functions. So from OpenGL.gl, we're just going to import everything. All right, the class mesh extends Object3D. To initialize, what do we need? Well, we already said we're going to need an instance of a geometry and a material. Okay, otherwise, there's going to be nothing to render. So we'll start off by calling initialization from the Object3D class. We'll store the geometry in a class variable. We'll store the material in a class variable. Again, a Boolean that answers the question, should this object be rendered? So self.visible, by default, yes, you should be rendered. Right, and then finally we want to perform that task. Since we've received a geometry and a material, we can now set up associations between the attributes in the geometry and variables, let's say shader variables, which are stored in the program in the material. All right, so I'll call this VAO ref. So OpenGL, go ahead and generate vertex arrays, just one. And then right away, let's go ahead and bind that vertex array. And every time that we've written a program, we've always had to go through this process of generating a vertex array and then binding it, and then calling associate variable on each of the attributes. This class is going to save us a lot of coding, a lot of typing, and a lot of time. All right, now I need a for loop for each variable name and attribute object. Now, there's a piece of information I have. I know what the geometry class is going to look like, so this might not make a lot of sense yet. But basically, the geometry class is going to contain a dictionary named attributes. And within the dictionary, I'm going to store each attribute by the name of the variable. So when I set up a for loop in this style, items returns both the keys and the values here. So in the dictionary, so it's getting both the variable name and the attribute object at the same time. It's extremely efficient. I should also move that up so you can read it. Again, the geometry class is going to store a dictionary called attributes. Items retrieves both names and the objects stored in that dictionary. So I need both of those as I'm iterating over them. And then for each attribute object in the dictionary, I'm going to call its associate variable method. Now remember, this needs the name of the program, or a reference to the program, and that's stored in the material. Right, so within this program, referenced by program ref, we're going to associate the variable with a name, variable name. Let's make that a little bit smaller. All right. So soon we'll never have to type this again. And then when we're done, just to clean things up, we're going to go ahead and unbind the vertex array object. Right, the way we can do that is by binding vertex array 0. Right, there is no vertex array object with ID 0, so that effectively unbinds it. Excellent. So these are the classes that we need. We have Object3D, and we have its 4 extensions, scene, group, camera, and mesh. Some of the next tasks are, well, we're going to have to create this geometry in this material class, right, for the different shapes you can see in the scene. And finally, we'll need to create a renderer class to kind of go through all those rendering steps, which we've done in every application so far. So the framework is coming along. In the next video, we'll start to talk about creating this geometry class.